Hello and welcome to our group's presentation on a Ceres sample return mission. My name is Kyle Brooks and I will be walking you through our project's design and results. The main idea for the mission can be broken down into 7 sections: Earth departure, interplanetary departure leg, Mars planetary flyby, Ceres arrival, mission and departure, interplanetary return leg, second Mars flyby, and the Earth return. Let's take a closer look at the mission and its elements. The first step is the launch from Earth. The specific space launch vehicle will be determined later. The launch vehicle first stage will place us into the desired parking orbit. We then begin our interplanetary transfer into Ceres. In order to reduce the amount of C3 needed, we will perform a planetary flyby with Mars. We arrive at Ceres and enter into near-polar sun-synchronous orbit. From there, we will land the spacecraft onto the surface. The craft will then collect samples. It will then ascend back up to commence its return trip to Earth. We will once more utilize the flyby with Mars, and then return the samples back to Earth. In order to design our mission, we will calculate our data with a combination of Hohmann transfer estimates, incorporated flyby theory, patch conics, and computer software. We will generate porkchop plots for determining our launch windows, delta V's, and optimal C3 values using MATLAB. With these values, we can use NASA's launch vehicle service programs to assist us in choosing our launch vehicle. Then FreeFlyer will help us develop a visualized trajectory for the spacecraft. We will also utilize Kerbal Space Program to generate 3D models of our mission for better visualization. Some key results we concluded while working on this project involve primarily our development of the porkchop plots and the mass calculations. In order to stay within our scope of the mission, we determined it was necessary to perform a planetary flyby with Mars. Furthermore, when selecting the launch vehicle and onboard engines, we quickly realized the importance of architecture for the landing segment of our mission. The masses play a vital role in these decisions. In order to fulfill the requirements of this mission, we have selected the Falcon Heavy Expendable because it allows us to carry more mass as a result of our calculated C3 value. The viable launch date will be between 2025 to 2035, and we are estimating that the mission will take approximately 12 years. The spacecraft will be powered by a bipropellant engine with a listed ISP for the descent and ascent phase at Ceres. Our spacecraft will utilize a cryogenic rocket engine because it will provide us with the required ISP needed to safely land and ascend from Ceres. For Earth departure, the launch date needed to be determined through the porkchop plots and the delta V was calculated. For the interplanetary departure, flyby flight time, arrival date, flyby delta V, flyby exit date, Ceres flight time, and arrival V were calculated. For the Ceres mission, we analyzed the capture delta V, sun-synchronous orbit parameters, spacecraft descent and ascent, and finally the departure date for Mars flyby. For the interplanetary return leg, the flyby time and arrival date to Mars, delta V, flight time, and velocity to Earth were calculated. For the Earth return segment, we had to make sure our entry velocity was less than 10 kilometers per second. The majority of calculations, such as the porkchop plots and the patch conics, were done in MATLAB. The JPL Horizons program was used to find the ephemeris data. The provided trajectory optimizer tool was used to sort out any anomalies in our calculated values. Our launch vehicle was selected by the NASA Launch Services Program, and as previously stated, FreeFlyer and Kerbal Space Program were used to model the trajectories of the spacecraft and generate visuals. To design our mission, we will be making a few key assumptions. First, we will assume that the launch vehicle will take care of all necessary plane changes and other parking orbit parameters. This ensures that once the SLV is selected, we only need to worry about the interplanetary transfer from the Earth parking orbit to Ceres. Next, we will also assume that once we arrive at Ceres, the vehicle will reserve enough fuel to correctly enter a polar sun-synchronous orbit. The amount of fuel will be determined later with our mass calculations. We will also need to ignore all external forces and moments on our craft with the exception of gravity. It will also be important to assume the mass of the sample is negligible relative to our spacecraft's mass. Lastly, we must assume that the cryogenic fuel for our onboard engine will not boil off for the duration of the mission. With these assumptions, we can apply Lambert's solution methodology, along with patch conic Hohmann transfers. Additionally, we will apply the use of porkchop plots as mentioned previously to determine some key parameters. The physical constants used in these calculations are listed in the slide, ranging from gravitational parameters to orbital radii of the bodies of interest around the Sun. In order to find the correct trajectory for the Earth-Mars Ceres transfer, MATLAB was employed to solve the Lambert problem. The code iterated upon all departure and flyby dates until the conditions produced a certain departure C3. From there, the code tests the Lambert problem against all possible flyby and arrival dates, where if the turn angle of the flyby orbit is less than the maximum turn angle possible, and if the magnitudes of the velocities at infinity match, then a solution is found. The function continues this calculation until all possible dates are tested. From there, a porkchop plot of the Earth-Mars trajectory is generated with the chosen C3 highlighted. This procedure was repeated for the return trajectory, Ceres Mars Earth, and other C3 plot was generated. All results were tested against with the trajectory optimizer tool to ensure accuracy. Using the V-infinity obtained from the MATLAB flyby finder, the delta V necessary to be captured into a 50-kilometer circular, polar, sun-synchronous orbit was found. In order to insert into the sun-synchronous orbit, 40 meters per second of delta V was allocated to correct any errors in the capture orbit. From here, 300 meters per second of delta V each was allocated for both ascent and descent of the spacecraft to account for the polar nature of the orbit and a safety factor for abort sequences. Finally, the burn of the return trajectory was calculated with the MATLAB flyby finder using the chosen C3 for the Ceres Mars-Earth flyby. Here, we can see the total values for our delta V. Using the total delta V gained from the previous calculations, it was decided a two-stage design was necessary. In order to obtain the required delta V, the spacecraft stages before ascending from Ceres in order to cut down on structural weight. The starting mass of the spacecraft was 8,000 kilograms, which the maximum the Falcon Heavy expendable can send on an energy orbit with a C3 of 33.5. This includes the mass of the second stage, which is 1,800 kilograms. The first stage only captures the spacecraft into an orbit around Ceres and lands the craft. From there, the second stage will power the craft back into orbit and send it on its return trajectory. The Free-Fire program was used as a proof of concept for our trajectories. If the trajectory matched the standard flight path of a flyby mission, then the estimations were accurate. Our trajectories proceeded as: the spacecraft leaves Earth on January 31, 2030 with a launch C3 of 33.58 and flies by Mars on February 20, 2032. From Mars it arrives to Ceres at November 17, 2033 with an arrival V-infinity of 4.65 kilometers per second. After orbiting Ceres for 5 years, the spacecraft begins the return trip September 3, 2038 with a launch C3 of 14.37 and returns to Mars for a flyby at August 13, 2040. From Mars, the spacecraft returns to Earth on October 3, 2041 with an arrival V-infinity of 9.55 kilometers per second. Below is where our spacecraft is estimated to land. The location was selected based on the low sloping nature to allow for a flat surface to land on. The final design of the spacecraft will have a total delta V of 8.8 kilometers per second. It will depart Earth on January 31, 2030, perform a Mars flyby, and arrive at Ceres on November 17, 2033, with an entry velocity of 4.65 kilometers per second. It will stay in Ceres, perform its mission for 5 years, and depart on September 3, 2038. The spacecraft will perform a Mars flyby and is estimated to arrive back on Earth on October 3, 2041. With an entry velocity of 9.55 kilometers per second. In conclusion, we have met the following objectives for this mission. We have designed the full mission to Ceres and return to Earth and also included in a Mars flyby. Our spacecraft will depart Earth in January 2030 and return in October 2041, which would mean a total mission time of less than 12 years. Our spacecraft will return to Earth at 9 kilometers per second, which is a bit high, but within range, and is within the 1,200 kilogram structural mass limit. It will use a cryogenic engine to provide for the thrust needed for a safe landing. However, we will not be able to return multiple samples since our spacecraft will not be able to go to different sites. To summarize, our timeline follows the mission from departure date of January 31, 2030. We will perform a Mars flyby on February 20, 2032, arrive at Ceres on November 17, 2033, depart again on September 3, 2038, execute a second flyby with Mars on August 13, 2040, and return to Earth safely, samples on board on October 13, 2041. Thank you for your time and have a great day.